Hello, everyone. I'd like to talk about a final exam review for Physics 120 for the students that I have in person taking a particular class called Physics 120. For anybody else who wants to look at this, they're free to do so. I plan at some point, at some juncture in the making of this film or films, I'm probably going to consolidate everything into one big film and then timestamp all the relevant, very important material so people can work through it. There is, for this class, we're doing basic Newtonian mechanics and some thermodynamics. The final exam about which I am talking about, the real final exam, is going to have problems associated with it. Obviously, you're taking a final exam, probably on the order of 40 problems. In this review for that final exam, there are 75 problems total. From those 75 problems, I will draw and have very similar problems from among those 75 problems representing the 40 problems in the final exam. Those of you who have me as a teacher and have dealt with me know this. I have said this very many times already, what I'm just saying right now. For anybody else who's not in my class, I mean, you're welcome to use the content that I'm going to try to bring forth. This is basic Newtonian mechanics, basic Newtonian physics, some thermodynamics in there, non-calculus treatment for the class at the institution at which I'm teaching, educational institution at which I'm teaching. It's called Physics 120. This is the final exam review. It's going to be comprised of 3 old exams, each one 25 questions long. So, there's 3 old exams, each one 25 questions long, 3 times 25. There's the 75 problems from which I will draw and get very similar problems for the final exam. The final exam on the order of 40 problems long. In the past, I was only giving 3 regular exams to make this happen. Other times and lately I give 4 exams, but the 4 exams that I would give in a class such as this, all that content previously was found in just 3 exams. So that's all. You're not missing anything. Okay. So there's something to look at. I'll try to timestamp this. I'll try to even, if possible, we'll see how this proceeds. I'll try to scroll the old exams and the solutions to the old exams at least at the very end of the film. So that's about where we are in regard to this. This is what we're going to do. Let's start the discussion with the first 25 of the 3 sets of 25 questions, 3 sets of 25 problems. Let's start with practice exam, or let's start with the old exam number 1. And we'll take it from there. Let's go for it. So, I mean, you have everything here. You come back to this. This is kind of your starting point. Give you an idea of what the structure is going to be, and let's proceed from there. So. Let's go for it. Let's go for it as best we can. Let's see how this proceeds. And I'll be erasing a lot of this pretty soon, and then we'll just go from there. For problem number 1, on planet Z, and again, this will all be scrolled. This is all for people in my class. They have full access to the old exams and full access to the solutions to the old exams. All the old exams and all their solutions are in Canvas for people in my class. As I said, I will try at some point somewhere in at least one place to scroll old exam number 1, old exam number 2, old exam number 3, which comprise the review for the final exam. I will try to scroll them somewhere in the video or videos. So you'll see it. Most likely at the very end of the video, you'll have access to all of this. Okay, is what the plan is. Exam number 1, as we have up here. Number 1, old exam number 1, fall 2019. Exam number 1, Physics 120. Problem number 1. On planet Z, the standard unit of length is the foot. And the astronaut is 5.2 feet tall on Earth. She lands on planet Z and is measured to be 88 foot tall. Foot is the plural of foot. Her partner Rachel is 92 foot tall. How tall is Rachel on Earth? Well, I mean, there's a lot of ways to go here. What they're saying basically is the units have to be at least consistent. There's no point in having units that are not consistent across the board in all kinds of measurements that are going to take place. If they're telling us, it's a straight out proportion on this one, if they're telling us that Ann is 5.2 feet tall and that's 82, so let's see here. So if Ann is 5.2 feet tall and that's equal to 88 foot, I'll just say F. I'll spell it out, I guess. Is that if the person who's with her is 92 of these foot tall, how tall is that person in feet? Well, the setup should be pretty straightforward, guys. I mean, there's a lot of ways, there are numerous ways you can set up a proportion. How much time do you have? And you can always verify that each way that you do it is going to give the same correct answer, no matter how you do it. So you look at this, and there's one way to do it is, I can say 5.2 feet is to x feet. This over this is the same as 88 over 92. Now I can reduce this, I can make things easier to look at. Let me just look at the solutions and kind of follow it pretty closely. As I said, you'll be seeing these as well, you guys. You play a little bit of the game with this, and you're going here, you're going here. We know how to do this, the cross multiplication. Absolutely true. At that point, divide by 88 on each side. And it's coming out to, okay, we suspected her friend was going to be taller because in the other system of measurement, it was a bigger number for her friend. So, for the fellow astronaut. So, I mean, that's, so it's 5.436 feet. And that's number 1. Number 2, see what they're doing here, guys. Kind of interesting here with the exam number 1, the practice exam number 1 for fall 2019, I have the solutions and the old exams stapled together. And so they're in one place. Whereas for the other ones, the exam and the solutions are separately posted. So, but they'll be right there in Canvas. There's no way you can miss it. 2, graphical addition. 2 vectors of magnitude 20 and 50 meters. So for graphical addition, 2 vectors of magnitudes 20 meters and 50 meters are added together. Which one of the following is not a possible value for the magnitude of the resultant? Well, if the 2 are added together, guys, I guess to find out the magnitude of the resultant, there are an infinite number of values that are possible for the magnitude of resultant. True, and there's also an infinite number of values that are not possible. I can't add 20 and 50 and get 100. I don't care how I do it. And I can't subtract 20 from 50 and get an answer of negative 100 or something, or something else. You're kind of locked into something. The biggest it can be in terms of magnitude is 20 and 50 added together. The smallest it can be in terms of magnitude is 50 minus 20, which is 30. So basically, the resultant vector, the magnitude of the resultant vector, sounds kind of a little on the odd side, is going to be greater than or equal to 30 and less than or equal to 70. So anything, any real number between there is absolutely theoretically possible. So we look at it and they say, okay, well, it's going to be something like that. What's not possible? Well, they're giving us options here. The options are 60, 50, 40, 25, 35. Well, wait a minute. 35 is okay, 40 is okay, 50 is okay, 60 is okay. They're all between 30. They're all between 30 and 70, including 30 and 70. They're all between 30 and 70. The 60, the 50, the 40, the 35, absolutely. 25 is not possible. So 25 is not allowed. So D, 25 meters, not allowed. Okay, that's number 2. Number 3, the length of each side of a square, is 20 meters. What is the length of the diagonal of the square? Pretty straightforward stuff. Pythagorean theorem. I mean, if it's 20 meters by 20 meters by 20 meters, it's a square. It's, all sides are congruent to one another. If I wanted to find this length right here, that is the hypotenuse. This is A, this is B. C squared equals A squared plus B squared. C squared equals 20 squared plus 20 squared. 400 plus 400. 800 here. Get the square root of each side. Square root of 800. Well, okay, what about it? Well, there's a number of ways you can do it. I mean, if C equals the square root of 800, we know that 800 is 2 times 400. That's the same as the square root of 400 times the square root of 2. The root of a product is the product of the roots. We've got this. This will come out to about 28.28. Let's see where they're going with that. And indeed, that's where they're going. I mean, this is more mathematically, I guess, the more rigorous way to give the answer on that. So it's coming out at the end of the day, it's going to be 28.28 meters. So you're looking at this stuff, guys. You're looking at this. Same thing here. Okay, let's go. Let's go to number 4. We'll take it from there. Let me just pause this a little bit and set everything up. But again, look where we are, look where we're staying, and I'll tell you when we move on beyond this. So let's just pause this and kind of just get right back to it. Okay, everyone. Let's continue. Let's look at number 4 and onwards. From Physics 120, Fall 2019, exam number 1. Of the 3 exams, of the 3 old exams, of the 3 old exams that we're talking about that comprise the review for the final exam, we're dealing with exam number 1 from 2019. Later on, we'll be doing exam number 2 from 2019, and then later on, exam number 3 from 2019. And 25 problems in one exam like that, exam number 1, 25 problems in exam number 2, and 25 problems in exam number 3 of the old ones from 2019. Total of 75 problems. From there we draw, okay, and figure out what we're going to be doing. So, okay, we're in pretty good shape here. Number 4, water flows into a swimming pool at a rate of 7 gallons per minute. The pool is 17 feet wide, 32 feet long, and 7 feet deep. How long does it take it to fill? They say a lot here, so we're gonna say a lot. So let's see what we can do. So what we're talking about is the rate at which this thing is flowing. I mean, I'll just say rate R is 7 gallons per minute. That's interesting. Okay, 7 gallons per minute. They're telling us the pool has a width of, let's see here, guys. I'm not seeing this too well. Okay, there it is. I see it right in front of me now. 17 feet wide, 32 feet long, and 7 feet deep. The deep I'll call H. I'll call it height. Height from the bottom, I guess you could say. 17, 32, and 7 in terms of feet. It's doing this many gallons per minute. It's a very basic concept how this is going to play out. The challenge is, well, I mean, we'll take a look at the challenge. You've got to be careful, not do anything careless. 1 U.S. gallon, you guys, is 231 cubic inches. And they write it a little differently, so forgive me on that one. So you guys, the big challenge here is 1 U.S. gallon is 231 cubic inches. Now, we've got to figure this out, and we've got to be careful, and there's a number of ways to do it. Let me see how I did it in the solutions. I probably want to stay close to what I did in the solutions to keep some kind of consistency here. You don't necessarily have to do that. The only obligation that you have is to do this right. I'll tell you what I'm going to do. The way I had done it was I kept it in terms of feet. Now you got to be extremely careful, guys. And this I guess we can kill 2 birds with 1 stone, or actually a bunch of birds with 1 stone we can do here. We know that 1 foot is 12 inches. 1 square foot, which is the way they write it like this. I say 1 square foot. If you square 1 foot, you're squaring 12 inches. You're going 12 inches by 12 inches. You're getting 144 square inches. You've got this. You've got this. So you've got this so far. Well, okay, I kind of jumped the gun here, guys, but okay, here we go. We got this for square. 144 square inches is 1 square foot. 1 foot is 12 inches. That's great. It's not really getting me to the end of where I want to go, but we're about to get there in a second. We know that 1 cubic foot is 1 foot by 1 foot by 1 foot, which is equal to 12 inches by 12 inches by 12 inches. Well, okay. There's a lot here. I mean, you know, how it's going to go. I don't think I actually did this. I have a calculator, I think, somewhere here. I might have to look at it. For some reason, I didn't do it with the calculator, but that's all right. This thing, what the heck? We got this far. We might as well go for it. 12 times 12 is 144. Times 12 is 1,440 plus 288. That's 1,728, I think. We're going to have to, for some reason, I did this a little differently. Not much. It's basically the same thing going on here. Let's make sure we got this. This is where the whole thing is going to happen. Just make sure we did it right, though, guys. I almost, rather than look for my calculator, I might as well just multiply this out. I got 144 times 12 here. Let's see, we got 288, as we said. We got this. We got 8. We got 12. We got 17. Yeah, there it is. 1728. So we're doing good. So, I mean, that's important. This is kind of what makes the whole thing happen. So it makes the whole thing happen, you guys. So what you're going to do is you're going to say, I'll tell you what. Okay, why is he doing this? If I can somehow figure out the total volume in terms of cubic feet, and then find out the rate of flow in terms of cubic feet, that's a big move. In other words, you're basically going 231 cubic inches multiplied by the conversion factor, 1 cubic foot over 12 to the third square inches. Well, we already, 12 to the third square inches was, cubic inches rather, I'm sorry. 1 cubic foot divided by 12 to the third cubic inches. 12 to the third cubic inches is the 1728 cubic inches. This will go ahead, do the multiplication here, and we're basically finding out, I mean, there's a number of ways to go, and that's 1 gallon is that. So they're saying that at the end of the day, and this is 1 gallon, so we're saying this 231 is 1 gallon. So we're saying that 1 gallon is 231 cubic inches. Yeah, and then we did this song and dance right here, wherever that's going to come out to. And that comes out to, at the end of the day, 1 gallon itself, you guys, is, according to this, I mean, if this is 1 gallon, you do this song and dance here, you're going to get cubic feet. You get 0.13368 cubic feet. Okay, that's kind of the real big move. Before you even do it, people are saying, okay, why all this? Well, we know the basic idea is this. Find how much volume has to be filled. Then find out how much volume is going in per unit time. Divide the total volume by the volume per unit time, and you'll know how much time it takes to fill everything. That's kind of the premise. Once you got to here, though, you guys, this is a big move. Once this is where it's at for this, and that's this. The 1 gallon is this many cubic feet. It's almost counterintuitive. Yeah, 1 gallon, that's a lot. Well, yeah, it is. Notice a cubic foot doesn't seem to be something too big. It's actually on the order of 1/7 or 1/8 of a cubic foot is what a gallon is. So it's kind of, it almost looks a little counterintuitive. But that's a big move. Once we know this, we got it straight. We got the whole thing straight. We can basically keep this thing. You could have done this a lot of ways. You could have converted all this stuff to inches, which is probably some pretty big numbers that are on the unwieldy side of what's going on. But so we'll see. We'll see. Let me see something here really quickly, guys. I want to make sure this is all printing out okay. Yeah, it is. Okay. All right. So it just seems like the number is a little more reasonable this way. So the volume is going to be, the volume under consideration, folks, is going to be, volume is length times width times height. That's the volume, length times width times height. Length times width times height, or width times length times height, who cares? Multiply them all together and see what you can do. Like I said, this stuff's a little easier done than said. See what we can do. If you actually do this multiplication right here, you're going to get the whole volume. If we're going to call Q, let's call capital Q the rate of flow. If we're going to call Q the rate of flow, then it's the total volume divided by time. And if you want to solve for time, this is the rate of flow, Q. This is the total volume, and this is the time it takes for the total volume to get filled. Total volume divided by total time will give you the rate of flow. If I want to solve for T, I multiply by T on each side and divide by Q. And there's other ways to do this, probably a little more clear than this, but I'm trying to stay with the solutions here. Use your instinct. The big thing is this. Find the volume that's got to get filled and divide it by the rate at which it is being filled. When you divide it by the rate, when you divide the total volume by the rate at which it's being filled, you'll find the time. It's as easy as that. You take it from there any way you want. You may want to do it a little differently than this when you're doing it. So let's see how you're going to do that. So you're going to go length times width times height. Length times width times height is 3,808 cubic feet. I'm staying with the cubic feet. The flow rate is, how do you want to go here? Probably got to take some of this out of here. Again, this is a lot easier done than said. When you're doing these guys, all these problems, you're not running across 30 or 40 feet of a room. You're doing it on pencil and paper, and you don't have to deliver a speech when you're doing it. That's the teacher's job. When you do this, you're doing it on paper, and you just got to make it make sense to yourself. It's a little different dynamic when you try to explain this stuff, obviously, right? But we can say this. If the rate of flow, they call it R. I know I called it Q over here. I mean, we just easily call this, R equals Q. We can do that too if you want. 7 gallons per minute. Let me see how we want to do this. 7 gallons per minute. And you've got 0.133. It is about proportions, folks. Proportions determine so much of what goes on in mathematics, whether we know it or not, whether it's explicitly said or not. Rate at which things are happening plays such a huge role in what goes on in mathematics and physics. So be on top of it. Know what's going on, guys. We got 0.13368 feet squared equals 1 gallon per gallon. You know where I'm going with this. They cancel. At the end of the day, the R being equal to the Q that I have way over there is going to be this multiplication. And it comes out to, as we said, 0.9358. 0.9358 Yeah, there it is. Well, okay, then go ahead and use it, please. I mean, we got this. We said it's equal to this. Let's go over here, 0.9358. Well, the cubic feet are going to go per minute. The amount of volume that has to be filled is 3,808 cubic feet. The rate at which it is being filled is 0.9358, a little less than 1 cubic foot per minute. How many times that going to here is going to tell you how many minutes it is. It's as simple as that. Like I said, it's usually easier done than said and maybe explained at some point. Let me just see something, guys, here. Right, okay, right. So what you do here at the end of the day is 4,069.4 minutes. It's good enough for me. I think they might have been talking about it. Now, they might be asking you for hours, so you better figure this out. Now, I wrote MI. It almost looks like miles per hour, so I shouldn't have done that. So please be aware of that when you're looking at this. I will convert the minutes to hours by doing the following. 4069.4 minutes divided by 60 minutes. Every time I got 60 minutes, guys, I got an hour. You got to divide by 60. You don't want the hours to be a bigger number. You're not going to divide it the other way around, an hour over 60, and get something huge on the order of, I don't know, 24,000. How on earth can it be 24,000 hours when it's only 4,000 minutes? So you got to divide it the right way. Again, it's about the proportions, knowing what's going on. And I think the way we did it was, let me just see how they answered some of this stuff. T is 67.8. It's a long time. 67.8 hours. How many days is that? Well, it's just short of 3 days, I guess, right? At that rate, at least. So that was number 4. Yeah, and I got 60, yeah, and right there, I've got it for you. 67.8 hours. We're talking about that. So the final answer here, guys. Again, you have to look at how they're asking you to answer the question. Yeah, you may have the right answer in terms of minutes, but if they want hours, you better make it into hours and know how to do the conversion. If they want days, you better know days. You want, I don't know, somebody's going to call this years. That'd be kind of crazy, but I guess you can call it years too. You know, 1 over 120 years, you know, 120th years maybe or something like that is how it'd come out to or something. But anyway, that's what it's looking at. So that's number 4. Let's move on a bit. Okay, guys, let's continue. Let's go to number 5. Same Physics 120 Fall 2029. Forgive me. Same Physics 120 Fall 2019, rather, exam number 1. Same old exam number 1 we're doing with here. Number 5, when NASA was communicating with astronauts on the moon, the time from sending on the Earth, to receiving on the moon was 1.28 seconds. Find the distance from Earth to moon. The speed of radio waves is 3 times 10 to the 8 meters per second. That's the speed of light. Pretty straightforward stuff. Basically, distance traveled equals speed times time. Don't know the distance. Do know that radio waves go at the speed of light, 3 times 10 to the 8th meters per second. It's going 1.28 seconds. And there it is. And let's see how the numbers go, how they like to report this. We got 3.84 times 10 to the 8th meters. Yeah, true answer. Kilometers, you need 1,000 times less of those because they're 1,000 times bigger. So divide this by 1,000, and you got kilometers. I think that's the way they're asking for the question to be answered. You're getting this. That can also be written as 384,000. So here we are. The same thing. Okay? Let's go to 6. Number 6. A train, let me just write it down at least. A train slowly climbs a 400-meter mountain track, which is at an angle of 8 degrees with respect to the horizontal. How much altitude does it gain? Okay, let's talk again. A train slowly climbs a 400-meter mountain track, which is at an angle of 8 degrees with respect to the horizontal. How much altitude does it gain? It's, you know, old school problem on that one. I mean, what you got here is, we kind of exaggerate the angle a little bit, if you don't mind. If this is theta equals 8 degrees, and this is going to travel 400 meters. What is the altitude here? H. Well, H over 400 is the sine of theta. H over 400 is the sine of 8 degrees multiplied by 400 on each side. Right here, they're going to give you the altitude. At the end of the day, you play the game here, guys. It comes out, H comes out to 55.67 meters. That's the climb, altitude-wise. Again, the 400 is right here. The sine 8 degrees is right there. And here we go. Okay. Let's go to 7. Let me erase this and actually put it up there. For number 7, a cheetah can maintain its maximum speed of 96 kilometers per hour for 26 seconds. What minimum distance must a gazelle running at 85 kilometers per hour be ahead of the cheetah to escape? Fascinating question. So for number 7, the cheetah can maintain the maximum speed at 96 kilometers per hour for 26 seconds. It'll cover a distance d when it's going a particular speed. You know, we'll say covers a distance d, rate of speed of the cheetah, r sub c, for a particular time that long. The cheetah, you know, what's the minimum distance? What minimum distance must the gazelle running this much be ahead of the cheetah to escape? Well, we got to find a number of things here, guys. So there's got to be like a minimum distance that they're ahead. See exactly how we did this. This could be done a number of ways. Let me consult the notes just to make sure I'm kind of staying the same way here on this stuff. The way we look at it is, how fast is the cheetah going? You know, rate of speed of the cheetah, or v sub c, I think I'm using in actual notes, and that's the gazelle. For that same period of time, you got to be able to stay ahead of it. So, okay, that's pretty interesting. You're using a little different argument than I'm using here. So, in other words, let's say the chase starts and people are going. Let's say that the chase starts and the animals are going at their respective speeds, which are like amazing speeds that you see in the animal kingdom. How do you want to play this? Well, look, maybe we should talk about conversion of units first and kind of take it from there if we want to do it. There's a number of ways you can go here. You can stay with the symbolic symbolism, the purely non-numeric symbolism, and then eventually get there. Or let's see what we can do here. The cheetah, v of the cheetah is 96 kilometers per hour. That's equal to 96,000 meters for every hour. Every hour has 3,600 seconds. Let's get this thing at meters per second because they're talking to us about seconds. And realistically, they're not going to be kilometers apart from each other. So let's keep it at meters. But since they're talking about seconds, let's figure this out. The v of the cheetah, v sub c, is 26.67 meters per second. So So here's v of the cheetah, which is just an amazing speed, guys. I mean, it's truly amazing. And let's just find the speed of the gazelle too, in terms of that, and we'll kind of take it from there when we can actually do it. Let's see. Let's get there. Let's go to that. When you're talking about the gazelle, I think they're saying it's 85 kilometers per hour, which is 85,000 meters per hour. An hour's got 60 minutes. Each one of the 60 minutes has 60 seconds. That's where I got the 3,600 seconds, you guys, when we first did this. The v sub g then at that point, it's going to be smaller, both just amazing speeds. 23.61 meters per second. Okay. Look, if they start dead even, this is a race that the gazelle loses, and loses it, and it for really bad consequences. This race, the only way the gazelle gets out of this is with a head start. If they start dead even, the gazelle's going to lose, according to the numbers here. So let's talk about it. What kind of a head start does the gazelle have to have? And like I said, let me kind of use the same units I'm using in my solutions, guys. So I want to be kind of consistent when I do this. And there's a number of things that can be said, and I'm not sure I want to go to the number of things just yet. But let's start here. Let's see if this is something. Let's assume the race is probably going to take place over that 28-second period of time. Let me see here. Yeah, you can do this for 26 seconds rather. Well, I think this is all going to take place within that 26-second framework, where we're assuming they're both going to be able to attain and keep maximum speed within that time frame and last during that time frame. VCT equals D plus VGT. So here's what I mean. The cheetah can run real fast. We know that. That's the ground it's going to cover in t seconds. The gazelle is going to cover, in that same amount of time, less distance. So it has to have a head start. Has to have a head start. The D is right in front in the actual notes here, but whether it's in front or behind, that doesn't really matter too much. Okay, actually, it's still here. All right, so from there you can find out what kind of a head start has to be done. If you subtract VGT on each side, so you got D is going to be equal to, if you subtract VGT on each side, see what happens here. I think what they're doing is they're assuming it's a 26-second race. And you're not going to get caught until the hope is for the gazelle that the gazelle does not get caught in that 26-second race. 26.67 minus 23.61. 26.67 minus 23.61 for 26 seconds. Yeah, and that's what D is going to be at the end of the day. Well, if you've got this head start, he can barely catch up to you, but maybe not going to catch you. You want to be at least 79.6. 79.6 meters of a head start before the chase begins, before the race begins and chase begins. So we're talking about that. That's number 7. Neat stuff. Number 8. A European sports car dealer claims that his product will accelerate at a constant rate from rest to a speed of 100 kilometers per hour in 8 seconds. What is the speed after the first 4 seconds of acceleration? Hint, first convert speed to meters per second. They're making a claim here. The problem perhaps looks more complicated than it is for us to actually solve it. But that's part of the challenge of any problem, folks. That's part of the challenge of any problem that you're going to be doing. You got to try to look through the language and see, is it easier than what they're maybe making it look like. The European, for number 8, a European sports car dealer claims that his product will accelerate at a constant rate from rest of 100 kilometers per hour in 8 seconds. Well, the acceleration is going to be 100 kilometers per hour per 8 seconds. Well, okay, that's a little bit, there's a little bit of conversion that's got to go on this thing. 100 kilometers on the top here is 100,000 meters per hour. We've already discussed that 60 minutes in an hour and 60 seconds. 60 minutes in an hour and 60 seconds in every minute it's a lot. I mean, it's a lot of stuff going on here, guys. But, you know, the 8 goes into here. It's 8 times the 36, which is, you know, going to be 288 at the end of the day. Forgive me. Yeah, it's going to be 288. It's going to be 24,880 divided by, let me just make sure. Again, I'm trying to do some of this stuff in my head, and it might not be the wisest decision on earth. But let's see what we got here. I got 288 and then 2 zeros on there. Yeah, I mean, so got this. Goes in here about 3 something, you know, close to 4. And let's see where that's going to go. That's going to be the acceleration. Once you've got, we're assuming a constant acceleration throughout the process to be able to solve the problem. And we'll take it from there. Right, okay. So we got it going to here, you guys. I did this a number of ways. I'm not even sure this was the best way to have done it, but the way I did it here was different than what I'm actually showing here. Yeah, it's very, very odd how I did this. Let me try to think here. Yeah, I did this completely in a different manner than what I'm showing you. I think that what I'm showing you is actually a better way to do it. Let's figure that out. Let's figure out what this is. Let me just kind of do something here, and then maybe I can show you the other way to do it as well. Yeah, I figured out. Yeah, whatever. It's okay what I did. I just maybe should have done what I'm doing right here. I mean, this is better. When at the end of the day here, you could this mathematics here. I mean, you could factor 100 out of here and factor 100 out of there, and you got 1,000 over 288. Factor a 4 out of here, you got 250. Factor a 4 out of here, you got 72. There's a lot going on here. Let's just make sure I'm doing this. I don't want to get too cavalier here. I'm going different from what I showed. Yeah, you just basically, you factor 100 out of here, you factor 100 out of there, and you got this. You factor a 4 out of here, you factor a 4 out of there, that's fine. You put a 2 out of here, you got 36. Put a 2 out of here, you got 125. So there's your acceleration. You got basically, let me leave it in terms of fractions. You got 125 over 36 for the acceleration. And then you go, okay, well, what's the final speed after 4 seconds? Final speed after 4 seconds is 125 over 36 times 4. this is probably the better way I could have done it, but I got 125 out of 9. You know, at the end of the day here, 9 goes in here. Interesting amount of times, guys. Let me see here. I don't want to say 14 times because it's not going to be 14. Or is it? Awfully close to it. So let me see what I got here, guys. Let me pull out the calculator here. We got this. Let me see what I'm actually going to say here on this. I have another calculator here, but I'll do this one. Yeah, 13 and 8/9. I mean, this is going to go into here 13 times. 117 is 8 short. Yeah, it's going to be 13 and 8/9. Roughly 13.89. And that's essentially 13.89, 13.9. This is probably the best way to have done it, guys. I did it a little differently in my notes. At the end of the day, everyone, the final speed after that would be this. And it's probably the best way to go. 13.89 or 13.9 meters per second. And that does it. I think the way I had done it, I mean, since I'd done it a little differently on this, to show it consistent with what's scrolling or what is going to be scrolling, guys, you've got this, the 13.89. How else could you take a look at this thing and make it happen? Well, I mean, the way I did it was, okay. I mean, the way that I just did it is probably the best way to have done it. It's not the way that I did it when I did the answer key for that particular exam. But what I did for that particular exam is still fine in that particular answer key. You're looking at it. They're saying something. I'm saying something different. I'm saying, okay, well, yeah, just the whole thing here. I guess the way you could have done it, maybe it is faster. I don't even know. You could say, look, for number 8, you could have said 100 kilometers per hour. We did the whole song and dance with, this is what we already did. That's meters per 3,600 seconds. That's 27.78 meters per second for a top speed. If you're going to play this game, VF equals VI plus AT. And the VI, you started from a dead stop, so the VI is 0. VF equals AT. Yeah, this is essentially the same thing, guys. I mean, they're saying you can make a final speed, and this guy's the final speed. This is the VF we're talking about. So there's your VF right there. This 27.78 acceleration associated with 8 seconds. When you do the division, you know, when you do the division there, guys, you find where you're at. I mean, you can kind of say, yeah, it's kind of an interesting point. Here's how I kind of got around it. If this guy's making VF right here, the final speed, which is 27.78 meters per second. If the acceleration, the same acceleration is going to take place, but not for 8 seconds, because t is 8 seconds, and t over 2 is the 4 seconds that this thing's going. This guy's, if you go t over 2 here, this is going to be half the final. Well, wait a minute. The final we said was 27.78. So half of that, half the final is where this thing's going. That's kind of the game. That was kind of the game. They're saying, okay, if this is 27.78 with an acceleration a for 8 seconds, if the same acceleration is taking place but only for half the time, if you divided this by half, you got to divide that by half. 27.78 is 13.89. And that's where I got that. I'm not sure what motivated me to solve it like that, but that is valid. It's valid. It works. It works. So you have that, you guys. That was 8. Let's move onwards. Let me put a pause on this and actually, erase this, and we'll start it up again at 9. Okay, guys, let's keep going. Number 9 is still exam number 1. Suppose a particle is moving along a straight line with a speed v for a time t, then stops for a time t, and then resumes moving along the original direction, and then resumes, and then stops for a time. So in other words, suppose a particle is moving along a straight line with a speed v for a time t, then stops completely, you guys, for a time t as well. So for t it was moving, and then for t it stops. And then resumes moving along the original direction with speed v for time t. What has been the average speed of the particle for the total time period 3t? Well, the thing was moving. Well, let's figure this out. I mean, I guess we could figure out that the average speed is going to be the total distance divided by the total time. Well, yeah. I mean, so what's going on here? What's going on is it's going in a straight line for a time t at a speed v. Then it stops and does nothing for a time t. Then it starts up again and does the same thing that it did very early on. T plus t plus t is 3t. You add these together, you get 2v. Vt and Vt is 2Vt over 3t. The t's cancel. Interesting problem. Okay, and there it is. Number 10. A car starts from rest. So let me write this down here. It might be easier for when I'm time stamping this to actually put something on here. Number 10, a car starting from rest accelerates in a straight line path at a constant rate of 4 meters per second per second. How far will the car travel in 10 seconds? Here we go. Car starting from rest, huh? VI equals 0. VI equals 0, and that's, I go for 10 seconds. Yeah, but the VI is 0. Plus 1/2 4 meters per second. And it's doing this for 10 seconds. Here goes. Half of 4 is 2. 10 squared is 100. There it is. 200 meters. 11. The minimum takeoff speed. 11, the minimum takeoff speed for a certain airplane is, again, the minimum takeoff speed for a certain airplane is 110 meters per second. What minimum acceleration is required if the plane must leave a runway of length 1,100 meters? Assume the plane starts from rest at one end of the runway. Well, that's an interesting point. So what you got here is, I would, if they're looking for acceleration, I'm probably going along these lines. They're looking for acceleration. They're not giving us the acceleration. So let's take an equation that has acceleration in it. Maybe we can manipulate it a little bit. Let me multiply by a on each side and divide by d. Let me multiply by a on each side and divide by d. So you multiply by a on each side, then you divide by d. The two's still there. Let's find out that acceleration. That might pull it off for us. It needs 110 as a final speed to get out of there. It starts at 0. Starts from rest. They're telling us that 2 is 2, and they're telling us that d is 1,100. It's a great question. There are tricks to how to do this, actually, but we'll cross that bridge as we need to cross it. You've got 110 squared. That's 110 times 110. That's just 0. We got the 1,100 going out of there. That's 11. I'm getting, just off the top of my head, I'm getting 5.5 meters per second, but don't necessarily quote me on that one. I'm just trying to jump to this. When you actually do this multiplication, let's just see exactly where this thing is going. Yeah, the 1,100, the 1,100 is going to cancel into this item squared, into this quantity squared. It's going to cancel into there just fine. And yeah, I'm pretty confident that's the way it's going to go, you guys. Let's see. Let me just check this for sure, guys, because a lot can happen. Everybody can make the mistakes. Just try to do it, guys. Try to be on top of this. And that was number 11. Yeah, 5.5 meters per second, you guys. Okay, looking good. Again, let's just start it up again. We'll go to number 12 in a little bit. Let me just pause this and we'll take it. We'll get to that. Okay, everyone, let's look at number 12 from exam number 1. Again, let's just keep going. A ball is thrown at 20 meters per second straight down from a tower and strikes the ground 250 meters below. Approximately how many seconds does it take the ball to strike the ground after being thrown? Neglect air resistance. Well, everybody's going in the same direction. So we don't have to worry about positive and negative when we're doing this stuff. We can just say, look, there is a height through which this ball will fall. There's an initial speed with which it is thrown. It'll take t amount of time for that to happen. And it is thrown straight down, so gravity's helping us. We're not going to call gravity negative. We're not going to call gravity negative when it's helping us. And we're going to go to here. Approximately how many seconds does it take for that to happen? Well, let's just see everything that's going on here. We are saying it's going to travel 250. Initial, these are all straight down. So if everybody's straight down, they're all negative, which means you can multiply by a -1 all the way across, and everybody's positive, and that's easier to deal with. You got this. I don't know what t is. I'm trying to find that out. Half of 9.8 is 4.9. Half of the 9.8 is 4.9. We got this. This has got quadratic equation written all over it. Just make sure I want to look at it just the way I'm looking at it too, so there's agreement when you're looking at some of this stuff. Yeah, that is it. I mean, you're looking basically at this, and you're saying, you're saying, okay, let me see what I can do here. I mean, let me write this thing somehow. Let me write it as 4.9 t squared plus 20t plus a negative 250 equals 0. Well, that looks a lot like ax squared plus bx plus c equals 0. What does that mean? Well, it means the usual. I mean, x, t equals x, I guess you could say. X is equal to the opposite of b plus or minus the square root of b squared minus 4ac, the whole thing, over 2a. That's x, and that's really what the t is. I'm going to get two answers here. Well, I don't want a negative time. I'm going to use the positive time when I get the answer. You carefully do what you got to do. Write everybody in terms of addition. Write everybody in terms of addition, because the quadratic formula is written in terms of addition. So make sure you're doing that right. So you got this. They're saying it's, there's a positive 20 there, huh? The opposite of positive 20 is, well, the opposite of positive 20. Plus or minus the square root of b squared minus 4ac. The a is 4.9. The c is negative 250. It's got to be done right, guys. If not, you've got to respect the way this stuff looks out. The way this plays out is it's ax squared plus bx plus c equals 0, and that's where this is coming from. There's no subtraction symbols present to solve this. Right here, the initial situation, everybody is written in terms of addition. It has to remain that way for you to be able to solve it. Divided by 2a, which is 2 times 4.9. Well, there's a lot goes on here. There's a plus, there's a minus. We're not gonna nickel and dime it. I don't really care about the minus, you guys. The t equals x, and it's equal to 5.39. 5.39 seconds. That's 12. Let's look at 13. 13 is saying a track star in the broad jump goes into the jump at 12 meters per second and launches himself at 26 degrees above the horizontal. How long is he in the air before running to Earth? How long is he in the air before returning to Earth? G is 9.8 meters per second per second. So the track star in the broad jump goes into the jump at 12 meters per second, and he launches himself at an angle of 26 degrees above the horizontal. How long is he in the air before returning to Earth? And then afterwards, in 14, what is the greatest height reached by the athlete for 14? And for 15, how far does he jump? So 13, 14, and 15, they're saying how long is he in the air for number 13? For 14, what's the greatest height reached by this athlete for 14? So 13, how long in the air for 13? What's the greatest height for 14? And for 15, how far does he go? 13, 14, and 15. How much time for 13? How high for 14? And 15, how far? How long a jump is it? All right, well, let's take a look. They're all together, so let's treat them all together. Let's talk about it. So for 13, we know from the equations that the total flight time is 2vi sine theta over g. End of the story. 2, he went into it at 12 meters per second. That's the vi. The sine of 26 degrees is what that is. And g is 9.8. The rest is math. The rest is arithmetic. Not really. I can't call the sine arithmetic, but the rest is just plug and chug. Let's go for it. 1.07 seconds. Sounds good to me. How high did they go? Well, I mean, we talked about that height situation. There's the derivation of it is pretty clear. It's been done a number of times. The height we're reaching here goes. VI is 12. Sine squared, get the sine of 26 degrees. When they got it like that, they want that quantity squared over 2 times 9.8. How high did they get? Pretty high. Very impressive. I mean, 1.41 1.41 meters. And that was 14. How far did they go? Well, that's that projectile problem. The person in question becomes the quote-unquote projectile at this point. They're launching themselves, and how far are they going? Well, according to this logic, we're going this way. We've got the 12. We got sine of 2 theta. Well, theta is 26. If you double it, you got 52. G is 9.8. Very impressive. According to this, I mean, it's pretty impressive how this is going to take place. We've got 11.6 meters. I don't think that's ever been done, honestly. I think the world record is short of 10 meters. So, but for the long jump, I think they're calling the long jump the broad jump, but whatever they want to say here. Very impressive, the whole process here, if you could do it. And I get, this is a very interesting point. I mean, just on the side here, I know we're just training to take a final exam, guys, but of interest, this 12 meters per second, the reason this number has not been attained, given everything else, if that were the takeoff, I guess it could happen if the person could make it at 12 meters per second. World's fastest human is not doing this in 12 meters per second. They're doing it in substantially less time than that. Maybe 11 meters per second, 10 meters per second, I'm not really sure. But 10 or 11 meters per second, it's not hitting 12, and that's why the 11.6 meters is not being hit. A lot of these numbers are not being hit. So that is 13, 14, and 15, how they closely relate to one another. Let's get it set up to go on a little bit further. Okay, guys, let's keep going. For 16, 17, and 18, we've done this in various classes that I've had throughout the years, including any class that I'm going to teach ever, regarding Physics 120, Newtonian mechanics. This just gets seen a lot. We've done this, you've seen me do it, and you've seen this on film in other places as well. They tell us to use the following information for problems 16 through 18. M1 is 100 kilograms, M2 is 300 kilograms, M3 is 400 kilograms, and you will assume that there's no friction, assume no friction, assume massless pulleys and massless rope. So the rope has no mass, the pulleys have no mass, and there's no friction. 16, 17, and 18. 16, what is the magnitude of the acceleration? 16, 17, 18, what's the magnitude of the acceleration? What is the magnitude of T1? What is the magnitude of T2? Find the acceleration for 16. Find the acceleration for 16. Find the tension associated with T1. Find the tension associated with T2. This has the most mass. It has the most weight. The acceleration is going to go downward. It's going to be acceleration A, the same acceleration A here, and the same acceleration A, but going upwards here. So you want to be aware of that. This is scenario 1, or circumstance 1, or location 1, no matter what you want to call it. This is circumstance 2, and this is circumstance 3. And we're gonna do what we've done in the past. The equations that derive from there, you've seen them before. Let's just kind of follow closely what I've said regarding that. And we'll take it from there. All right, so basically, guys, when you're looking at these scenarios, I mean, we've done this, you know, if you've been in my class, anybody who's been in my class has seen me do this. And you've seen this on films in other places when I'm trying to actually show how to do a lot of this stuff. So it's here, we know how to do it. We're looking at this and we're saying, okay, there's 3 equations we can get out of this. And you've seen me do this. You can see this in other videos as well. The conclusion from scenario, you know, you look at scenario 1, you look at scenario 2, and you look at scenario 3, and it's looking pretty good. I mean, it should come out with conclusions, as we've done in the past, of something looking like this. Three equations and 3 unknowns. This right here is M1A, is T1. I mean, this is a bit of an abbreviated look of where those 3 equations come from. But if we play it right, we should do all of what we've done in the past and be able to be looking at a situation looking a lot like this. Solve for T1 right here, and you'll have T1. Solve for T2 right here, you'll have T2. Solve for A by dividing by this coefficient on each side, and you'll have A. How that came about, like I said, we've done that in the past pretty heavily in other films and in person. But you should be able to get these 3 equations, which will take you there. If you divide by the coefficient of this guy on each side and plug in the numbers, so for 16, you're looking at the first scenario, number 1, you're going to have M3 minus M1 times G over this entire sum. Plug in all the numbers, the 400, the 100, the 200, the whole thing. The 400, the 100, like I said, we had the 200 as well. It should not, for some reason, I don't know why that's coming out to the number I'm getting here. I'm not 200 rather, it was 300 rather. It was the 100, the 400, the 300, okay. The 100, the 300, the 400, the 400 minus the 100 becomes 300 over 800 times all this. At the end of the day, guys, just plug in the numbers. Know what the equations are going for. There is Here's number 16 for you. For 17, you know, solve for T1. Add an M1G on each side. It becomes T1 equals M1G plus M1A. Well, that's just, you can factor it out, make it look like this. Plug in what you got for A. Plug in what you got for A there, and they're saying, well, it's 1,300. There's a lot of force here. Well, yeah, the masses are pretty big. To be moving with that kind of an acceleration, yeah, there's got to be a lot of forces, so don't be surprised. These are big numbers. Relatively big numbers, at least. So you got this. So that's the 17. 18. Same kind of situation. Why don't you solve for T2 on each side? Well, let me add a positive T2 on each side and subtract M3A. It's M3G minus M3A. M3G minus M3A. Well, I can just do some factorization and get right here, and that's T2. Plug in the numbers, grind out the answer. Yeah, I mean, we figured it was going to be a bigger, the more massive weight. If we're going to make the thing go clockwise, if this thing's going to go, is it clockwise or counterclockwise? Actually, in this situation, I guess it would be clockwise, wouldn't it? If it's going to go clockwise like this, yeah, I mean, the T2 is going to be bigger. And we're getting that answer. All right, guys. I mean, looking pretty good. 17 right here, 18 right there. Okay. Let's go 19 through 25. Let me pause this and set this up so we can go pretty efficiently, at least when you're viewing the film. All right, everyone. Let's do problems 19 and 20 really quickly. Number 19. A Hooke's law spring is compressed to distance d and is used to launch a particle of mass m vertically to a height h above its starting position. Under double the compression, the spring is now, so from the starting position, in other words, where it gets launched. So where it leaves, I guess we'll take it that way. After the spring's been extended to some extent, or at least come right out and just let it go. They're not playing too many games with us in this regard, guys, but let me look at it one more time. Number 19, a Hooke's law spring is compressed at distance d and is used to launch a particle of mass m vertically to a height h above its starting position. Under double the compression, the spring is now used to launch a particle of 2m. The first mass, you guys, was m. The second mass is 2m under double the compression. How high does the second mass rise above its starting position? So we're gonna use Occam's razor quite a bit when we're talking about this. We're not going to look at regarding starting position what we can say and what we cannot say regarding something like that. Let's talk a little bit. So basically, they're saying it is about energy conservation. So in other words, right when the mass, we'll call the starting position right where the mass leaves the spring. Right where the mass leaves the spring. 1/2 kx squared is the total potential energy. Well, the x happens to be d, so it's 1/2 kd squared. And that'll get me to a height mgh. When you do double now that's basically the way it is, the way they're asking this particular question. So let's kind of just be very very cautious, I guess, how we do something like this. What we're saying is, the Hooke's law spring is compressed at distance d and it's launched. The Hooke's law spring is compressed at distance d and is used to launch a particle of mass m vertically to a height h above its starting position. Under double the compression, you're going to now launch a particle which is twice as massive. How high does that second mass, twice as massive, rise above its starting position? So, look, this is the first situation with mass m. What does happen, indeed, when you compress something twice as much? All this right here will give you, when you wheel and deal with the mathematics, you end up getting 4 times, you wheel and deal with this. This is 4d squared. Bring the 4 out of there. It becomes 4 times the potential energy that was originally present when you only compressed at d. If you compress at 2d right now. So if that's the case, then if it's 4 times the potential energy, this is also going to be, these are both a measure of potential energy. These are both a measure of potential energy. So if this situation is 4 times what was going on earlier, then what's going on here would be, there's a number of ways to go here. What is going on here? It's a good question. What would it be with twice the mass? With twice the mass going on, and G, and I don't know, we'll call it capital H. I did it a little differently on the other thing here. The basic thing is, in the first scenario, this energy is equal, this potential energy is equal to this potential energy. And 4 times the potential energy will be equal to 4 times what this is. So in other words, if this is true, potential energy equals potential energy. Spring potential energy will give it gravitational potential energy. If you make the spring potential energy 4 times what it was initially, how'd you make it 4 times what it was initially? You compressed it twice as much, and you did the mathematics to get to here. Then this right here, for the mass that was just a single mass, a mass of m, you're going to get 4 times this as well. Well, sure, if that's the case, this right here, mgh, they're all equal to each other, is going to be equal to 2mg times some h. Well, wait a minute. This is 4mgh. This is 2mgh. I'm going to divide by 2mg on each side. I'm going to divide by 2mg on each side. There's a 2 here. The m and the g go. That 2m mass, you guys, the big 2m mass is going to go to double the height. It's going to go to double the height. So that's the situation there. 4 times the energy released, and we get that to be the case. And I wrote it out that way. So that's for 19, you guys. For the other one, how high, if you got 4 mgh going on, potential energy, right? Well, that's what the new situation is going to be. How high is the single mass going to go? Well, why don't you rearrange them a little bit and write it like this? For 20, the height for this 20 is going to be 4h. So y equals 4. I think I was using y to get there. But when we're talking about this, so it's almost like so many of these problems, you guys, like so many of these problems, this tends to be this tends to be easier done than said, I guess, and not necessarily that they're easy. You got to think it out a little bit. But if you've got 4 times the potential energy, well, for the same size mass, you're going to have 4 times the height. And that was, you'd almost wish they would have asked you problem number 20 in that regard, in that way. I mean, saying, okay, well, this is problem 20. You know, say, well, if you got 4 times the potential energy, when you compress it twice as much, it's going to go to 4 times the height to give you 4 times the potential energy. See, 4 times the potential energy in spring potential energy is going to equate to 4 times the potential energy in gravitational potential energy. Well, if it's the same size mass, same amount of mass, to have 4 times the potential energy, you've got to have 4 times the height. So this is number 20. So number 20 is almost an easier one to answer first. You're going 4 times the height. If you've got double the mass, well, that takes away, that comes into the equation for potential energy. So if this is 2m and the other one is 2h, 2 times 2 is 4, that'll also make it work. And we've got that. So that takes us through 20. We will do 21 through 25 shortly at some point. So let me leave this as is right now. Hello, everyone. Let's finish this up. Problem 21 and 22. Let's work our way all the way through 25 for the Physics 120 Fall 2019 exam number 1, which is the first part of 3 parts of the practice exam for the final exam. Number 21, multiple object accelerating systems. The figure shows a 100 kilogram block being released from rest from a height of 1 meter. It then takes 0.81 seconds for it to reach the floor. What is the magnitude of the acceleration of the mass m on the left? There is no friction or mass in the pulley, and the connecting rope is very light. So the way this plays out is essentially there's the pulley, massless rope, frictionless pulley as well. That's M. This is 100 kilograms. It's basically going to fall 1 meter. Let's see what happens. Well, I mean, look, guys, a lot of ways to look at this, but here's one way to look at it. If something travels, well, as we can say, there's a number of ways to go with this. Let's see what we could say. Don't know what the final speed of this is. That could be another question to ask, but right off the bat, without even looking at, or maybe we should look a little bit, to this right here, they're saying a number of things. Probably among the easiest ways to look at this is saying, okay, it's going to fall a distance d, VIT plus 1/2 GT squared. Since everybody is falling downward, we're going to call everybody positive. It is dropped from rest, so that's 0. VIT is 0. How'd they actually say that? I mean, the actual probably stapling the solutions, guys, and the actual practice test together may not be the greatest idea in the world, but here we are. So what we're saying here is it takes us about, it's released from rest. So that's kind of the big thing to look at. Well, if that's the case, so a lot can be said here, guys. I mean, so let's kind of say what we want to say. Released from rest, VI is equal to 0. Therefore, we're looking at this situation. Forgive me, I should not have said G on that because we don't know. We know there is a bit of a tug of war going on here. So please nix what I just said right there, guys. Don't go there. If you start it like that, it's initially the right idea, but this is not in free fall. You'd have G going on like I erroneously drew here. You'd have the G acceleration going on if you cut the rope right here, or if you cut the rope right there, it's going to fall at G. Otherwise, it's not going to happen. So let's do that again. Forgive me. It's going to be some A. I don't know what that is. D equals VIT plus 1/2 AT squared. It is released from rest, so VI is equal to 0. And this is the ticket right here, guys. How are you going to do it? Multiply by 2 on each side and divide by t squared. And A is going to be 2D. So you multiply by 2 on each side, and you divide by t squared. You got this, and let's see what we got here. That's it. I mean, the answer is going to be along these lines. Now let's just get it right. D is a fall of 1. The T is 0.81, and you're going to square it, and you know, that's where it's going to go. It's as simple as that. When you go for it this way, guys, you basically got this thing being squared, which is an interesting matter in its own right, correct? But you know, if you square it, it's going to be 0.6 something going into 2. Well, it's going to go in there 3 point something times, and that's going to give you the acceleration. So it's 3.05 meters per second squared. Absolutely. So we have that. The mistake I made initially was just going right to G. Well, G would be if there's a free fall. There's not really a free fall here, even though it's a massless pulley, frictionless pulley as well, and a massless rope. The fact that there's a tug of war going on, neither of these are going to move as though it's just a flat out G. It's going to be less than G. And that's where the A comes in, and then you play the game and you get the answer you get. Now, what's of interest regarding all that? Well, if you want to find out what the matter, I mean, it's an interesting matter in its own right. Now, you can also say, I mean, let me kind of, a little sidelight here. Nobody asked you this, but let's say they did. What is the final velocity before that thing hits the ground? It's this. It started from rest. VF is going to be this. VF is going to be 3.05 times 0.81 to get an answer there. Now, we never really, and this nobody asked us this, but let's, what the heck? We got this far, might as well do it. Somewhere on the order of 3.05 times 0.81. Kind of interesting how that's going to work out. So, I mean, at that point, like I said, I'm sure I have a calculator here somewhere, guys. If not, I don't. Again, nobody asked this second part that I'm kind of doing. They did ask 22, which is a different dynamic, different question being asked. But let's say we can say something. You got 3.05 times 0.81, 2.4705. Started from rest, it'll hit the ground. It'll hit the ground at 2.4705 meters per second. After 1 second, right before it hits the ground, it's going to hit the ground at 2.4705 meters per second. In that 1 second, this thing will climb 1 meter. Forgive me, not 1 second. In that amount of time, 0.81 seconds. So it'll hit the ground at 2.4705 meters per second after a fall of 0.81 seconds. So in 0.81 seconds it'll take 0.81 seconds for this to go a 1 meter fall. It'll travel 1 meter in 0.81 seconds. At the end of the 0.81 seconds, right before it hits the ground, it's going at 2.4705 meters per second. In that same 0.81 seconds, this mass M will have climbed 1 meter as well. And at the end of that 1 meter climb, it will also be traveling 2.4705 meters per second, only going upward where the other one was going downward. Okay. So, I mean, that's of interest. A little extra there. Nobody went there. They didn't ask us to go there. They did ask us to go here for 21. And then, like I said, this is just a little bit extra here, just on the side, get an idea what's going on, how to do a little bit of the discussion for this. Now, for 22, they did ask us, what is the mass M? Well, that's not that difficult to find out in a lot of ways, because you can say, look, whatever's going on here, this is, what's the, you can also find the tension. Now, nobody asked for the tension on this one either, but let's see here. You can make it a tension problem as well. For our purposes, let's just say this. This one's climbing with acceleration A, just like this one's falling with acceleration A. Let's look at both scenarios and find out what, we can look at both scenarios as one big scenario. I got one big scenario for you. Because m and 100 kilograms, those two are tied together, m plus 100 kilograms, the mass m plus 100 kilograms is one big mass moving with acceleration a. You were able to get this amount of unbalanced force from the tug of war of 100 g minus mg. It's basically doing this. M plus 100 times A is 100 here. Forgive me. Got this. Okay, I mean, there's a lot going on there. Let's try to figure out something so we can solve this. I mean, I'm trying to solve for m. They want me to solve for m now, right? This is what 22 is all about. You want me to be able to solve for m. Let me see what I can say here. How about I just distribute the a and get this? How about I distribute the g and get this? How about I take and add a positive mg on each side, and subtract 100a on each side? Okay, that's pretty interesting. Let's do the reverse. Let's do the reverse of the distributive principle. It's called factorization. We got this right here. We've got this right here. Let's divide by the quantity a plus g on each side. M is going to be this. It's going to be, M is going to be 100 g minus a over g plus a. So we got this. This is going to be 100. You got, whatever we got here, we got 9.8 minus what we said that was, which is 3.05. And here we got 9.8 plus 3.05. Okay, it's a little bit of a mess. Here's the 100. You do the subtraction here. You got 6.75 on top. And here you add, and you got 12.85. Okay. So that's about it. So what are you talking about here? We're getting over, let me just get up here, guys. Just write that again for emphasis, I guess you could say. you've got 100 times the ratio of 6.75 over 12.85. I mean, at some level, it seems to make some sense. I mean, it's a ratio, it's about the ratio of 1 over 2. 1 over 2 times 100 is about 50. Yeah, it makes sense that m's not going to be a big number compared to 100. Why? Because 100 won the tug of war, and it fell down that way. So you want to kind of look at it in that sense. Well, there's a whole lot here. I mean, to make the long story short, it's 52.5 kilograms. And that's for problem number 22. This one definitely we need as an answer. We have to get an answer for this. And we did. That's 21 and 22. You guys, let me just go straight through on this if I can. 52.5. Now let's go to 23. 23, a boat with mass 1,200 kilograms is traveling at 12 meters per second. What is the magnitude of the force required to stop the boat if it undergoes a displacement of 85 meters? Well, you got to stop this thing. What kind of force is required to stop this thing while there's a displacement of 85 meters? You got 85 meters to stop this thing. The boat has a mass of 1,200 kilograms. It's traveling at 12 meters per second initially. You got to bring it down to a dead stop, which is 0. What is the magnitude of the force required to stop the boat if it undergoes a displacement of 85 meters? Okay, so with that in mind, okay, let's see how this gets done. I mean, there's got to be, they want the magnitude of the force. You know, well, if it's massive and it's moving relatively fast, you know, there's stuff that has to be done. We know at the end of the day, force equals mass times acceleration. The acceleration this thing undergoes is of interest. I mean, you know, I guess we can play this a number of ways. I mean, to find the acceleration, it's VF minus VI over the time span that it took for that to take place. The thing is, it's hard to figure out what that time span was. I mean, you could look at it a bunch of ways. I mean, I guess there's things we could do and find out what, I mean, we could use D equals VIT plus 1/2 AT squared. Maybe a little more efficient is something like this. D equals VF squared minus VI squared over 2A. What do you say you multiply by A on each side and divide by D? That might do it. What you're trying to do here is you're trying to bring it to a dead stop. So VF is 0. You had it going at 12, and you're going to have this thing go, I think it was 85 meters. Let me just check on it again. 85 meters. So you got 2 times that distance, 2 times 85. Now it's a negative acceleration because you're putting the brakes on. You do the song and dance up here, you've got this. Down here, you got this. And that gives you the acceleration at the end of the day. Well, that's fine. It's going to be a negative number, but I just want the magnitude, so that's not going to be too big a deal. If you look at it, so for this right here, we got, the magnitude of this thing is 0.847 meters per second squared. The magnitude of it's negative 0.847 meters per second squared, But for our purposes, positive's fine. 0.847 meters per second squared. That's the magnitude of the vector. Well, that's great. If that's the case, that's kind of a done deal here. This thing right here, the mass of the boat is, was it 1,200 or 12,000? I think it's 12,000. It's got here 1,200. Okay, so that's good enough for me. The mass is 1,200. Magnitude of the acceleration (1,200 times 0.847), and we're getting the force is 1016.5. In other words, 1,016.5 newtons. Sounds good to me. That's 23. 24 is saying a pole vaulter clears 3.98 meters. With what speed did he strike the mat in the landing area? Well, he cleared 3.98 meters. With what speed does he strike? Well, I'd probably come back to this, to be honest with you. May not be. I mean, at second look, it may not be the way to go. But let's see what we can say about it. He's falling down when it's all done. With what speed does he strike? That is a good point. You could go here. This is true, and there's things we can do to make this work and get an answer for us. Perhaps a better answer is this. The pole vaulter has potential energy at the top of mgh. All of it is going to be converted to kinetic energy, and this is the way best way to do it. I can do stuff with this, but it would be a bit convoluted. It can be done, but in the end, it reduces to deriving something like this anyway. All the pole vaulters' potential energy will be converted to kinetic energy. From here, we can solve for V. Multiply by 2 on each side and divide by m on each side. So multiply by 2 on each side and divide by m on each side, you get V squared by itself. You multiply by 2 on each side, you divide by m, it's 2gh. Square root both sides. It's pretty neat. Well, I mean, at that point, it's just 2 times 9.8 times 3.98 meters. Go through the whole song and dance on that. Let's see what we got here. You multiply those, you do the whole thing here. Let's see where we were on that. Yeah, I mean, just do the whole, just do the whole song and dance on that whole thing, you guys. Take the product of 2 and 9.8 and 3.98 and square root the result of that product, and you'll get V is 8.83 meters per second. So, at the end of the day, V is 8.83 and that's that. 25 is perhaps more intimidating than it should be to anybody. It comes out a lot easier than what we might think. For problem number 25, let me erase this and we'll just go for it and we'll be done with this part of what we want to be doing. Okay, for number 25, a baseball outfielder throws a baseball of mass 0.36 kilograms at a speed of 34 meters per second and initial angle of 30 degrees. What is the kinetic energy of the baseball at the highest point of the trajectory? Well, this is interesting. Very interesting. What we're looking at basically, guys, what is the kinetic energy of the baseball at the highest point of the trajectory? At the highest point of the trajectory, my friends, doesn't matter the angle that it's thrown at the highest point of the trajectory, the only thing under consideration is the x component of velocity. It's not going up at the highest point. It's not going up because it's at the highest point of the trajectory. It's not going down because it's still at the highest point of the trajectory. It's a horizontal velocity component that is alive and well. And it's the only velocity component that's actually in play right now. This is the only velocity component that matters. It's the only velocity component that is. At the very top of the trajectory, it is the only velocity component. So all you got to do is just find out what Vx is. Well, wait a minute now. Isn't Vx V times the cosine of theta? Isn't Vx, we can say a lot of stuff here. I was throwing at 34. Cosine 30 degrees. We end up getting what that is. Now there's some tricks we can play with this whole thing where you to actually get the answer here. I don't know if I want to go there. I think I could probably create more problems for people than it would be help. But let's at least kind of look at the end of this thing where you want to take it. What you can say is, it's a very easy move, I guess you could say. You could say, okay, at the end of all this, I mean, we could take this thing what it is. What the heck? I mean, we don't need. I mean, we can multiply this out. The cosine of 30 degrees is actually going to be the square root of 3 over 2 in actuality. So, which is the zone dynamic. If you do it, it comes out to the square root of 3 over 2, which is something like 0.866. 0.866 times 34 comes out to something like 17 times the square root of 3. 2.8 something. I don't know. I'd have to look at it and knock it out. The real big thing here is don't worry about it until you need to worry about it. Let's get to the calculators when we need to get to the calculators. I guess the big thing I can tell you is this, guys. If kinetic energy, and I just told you what it is about, I'd have to kind of look at it. What the heck? I got this far. I might as well go through with it. Let me see what we got here. Now, I told you the answer was going to be the 17 times the square root of 3, which is going to be somewhere in the ballpark of between 2.8 and 3 as an answer here. Let's just see what we got. I may not have the cosine function here, guys, so this is, I do actually. 34 times the cosine. Let me see here, guys. There's got to be an easier way to do this, but let me see where I'm at. Right. For some reason, I had it on radians. And we got, what did we say? The answer was going to be somewhere in the ballpark. I think I said it wrong. I said something between 2.8 and 3. Actually, something between 28 and 30. It's 29.444. So basically, we didn't really need to go here. Eventually, we're going to get to the calculators and get the answers that we want to get. But let's go with this. So basically this right here, indeed, the cosine of 30 degrees is the square root of 3. The cosine of 30 degrees is the square root of 3 over 2. Square root of 3 over 2 times 34 is 17 times the square root of 3, and that comes out to 29.44. Okay. Goes something like this, I guess you could say. The kinetic energy, you guys, is 1/2 mass times the velocity. In this case, it's Vx squared. It's pretty simple at that point. Just let's be careful. They're saying that the mass is 0.34. They're saying that this right here is whatever, whatever that was going to be. Now, the way I wrote it out is I did all the calculations at the very end. I left it at 34 cosine 30 degrees, and then we squared it. 34 cosine 30 degrees, and then this whole thing got squared. That's fine. I mean, that's whatever you want. I mean, at that point, we have faith in what we gave as an answer there. We just put that in for Vx right here and then square that Vx. This would be the Vx, then square it, then go for it. Do all the mathematics that needs to be done, folks. And this one should have been, forgive me, it should have been 0.36. 0.36 kilograms is what that is. So we got all this. At the end of the day here, this comes out to 156.1 joules. 156.1 joules. And then you just, like I said, you make the appropriate choice when you're doing the multiple choice type questions. And we're looking good. Thank you. There will be at least one more film pertaining to these. This was exam number 1, practice exam number 1 of the old practice exams. Old practice exam number 1 from fall 2019. We just did it, 25 problems. We will do old practice exam from 2019, exam number 2, also 25 problems, and also old practice exam number 3 from 2019, also 25 problems. So all 75 problems will be in there. I'll have all the exams, all the old exams, and all 75 solutions fully solved for you and scrolling at the end of the appropriate video or videos. Probably, I'm thinking there's probably going to be 3 videos total, and all of those in their entirety will scroll at the end of each video. That's the plan if we can do it. All right, thank you all for your time, and take care.